We are now jumping into another main topic in calculus. We have looked at limits. Limits was a huge topic in calculus, and we used limits to help us define the derivative. Derivative was another big area in calculus. Now we're getting into antiderivatives, integration, and that's the last part of this class. And we've looked at a little bit of antiderivatives before in this chapter, but not too much. And I'm going to give you some tools in here on how to look at this. Okay, so right in front of us, you should see the definition of an antiderivative. So a function, capital F, is an antiderivative of lowercase f on an interval I if we take the derivative of f prime of x, we would get back little f of x for all x on I. Antiderivative, we will denote with a capital F. So capital F of x is the antiderivative of little f of x. So if it was capital G of x, then that would be, we would be representing the antiderivative of lowercase g of x, etc. And what this is saying is, if we look at the derivative, this is how we can test things, of the antiderivative, we should get back that original function, f of x. And so we're thinking backwards. We're thinking to ourselves, what can I take the derivative of to get this back? And so, for instance, let's just look at some easy cases, or maybe not easy cases, but kind of think backwards before we look at some giving you some tricks. Anyways, let's say, that's actually just because I just did it. Let's say that f of x is equal to 1. So think to yourself, what could I take the derivative of and get back 1? Well, remember, if we took the derivative of x, that gave us back 1. But we could take the derivative, right? If I took the derivative of this would give me back 1. But if I added any constant in here, c, where c is equal to a constant, and we took the derivative of this function now, taking the derivative, well, derivative of x is 1, and derivative of constant, remember, was 0. And so this would just give us back 1. And so we are going to add, when we're taking the antiderivative of a function, we're going to add this constant c. And I'll talk about that a little bit more in a minute, after we've kind of gone reversed and did a little more examples of why we are adding the c. There are times where we're going to be given information where we're going to be able to figure out what c is. But for now, we're just going to add the c in here. Okay, so let's look at some more examples. So let's say that g of x was equal to x cubed. And we want to figure out, what do we take the derivative of and get back x cubed? Well, we know when we took the derivative, we got 1 less power, right? Because we subtracted 1 from our exponent. And so if we're going to be taking the derivative and we're going to get back a cube, we know that this has to be a 4th power. But if we took the derivative of x to the 4th, right, we bring our exponent down and then we subtracted 1 from our exponent. So right now, if we took the derivative, we would have this 4x cubed. But our original function, right, doesn't have that 4 in there. So we need something that's going to take care of it. It's going to cancel it out. And so if we divide by our exponent of 4, our new exponent, then now when we take that derivative, bringing down that exponent of 4 is going to cancel with the 4 in our denominator. So capital G of x equals x to the 4th over 4, and then we're going to add some constant c. Let's say we had h of x, and I don't know, let's say we had 2x to the 5th plus the square root of x minus 2. So could we figure out what we could take the derivative of to get that h of x back? Actually, before we do that, let's rewrite this function a little bit, right? Let's rewrite that square root of x without the radical and with the rational exponent. So we have h of x is equal to 2x to the 5th plus x raised to the 1/2 power minus 2. Okay, so thinking to yourself, what could we take the derivative of and get back 2x to the 5th? Well, we know when we take the derivative, we're going to have one less in our exponent. And so for the 5th power, to get back a 5th power, we know that we're going to need a 6th power. So we're going to have an x to the 6 here. Well, when we bring that power down, right, it would be multiplied to this 2 out here. And that, when I take the derivative, that would have given me a 12x to the 6. But I don't want that 12x to the 6. So let's divide by this exponent of 6. And let's just leave that 2 out here. Would that work? Yeah. Okay. So when I took the derivative, the 6 would come down. It would cancel with the 6 in the denominator. It would give me back this 2x to the 5th. Okay, so we need 1 extra in our exponent so that when we subtract 1 and when we take the derivative, we get 1/2. And so getting 1 more in our exponent than 1/2. So let's add 1 to our exponent. Well, adding 1 to 1/2, so 2/2. That would give me a 3/2 power. So notice when I bring it down, that when I take the derivative, I would have a 3/2 in front. But this has a coefficient of 1 in front. And so I need something that would counteract that when I bring down that exponent. And so I can think of it as dividing. I usually won't do it this way, but I can think of it as dividing by my new exponent of 3/2. We'll clean this up in a minute. Minus, so what do we take the derivative of to get back to? Well, to get back a constant, just the constant, then we had that constant times x. And then plus c. So let's just rewrite this really quickly, cleaning it up, and then let's show that what we have is correct. So notice we have a 2/6 coefficient in front of that x to the 6, that reduces. So we can say that this is the same thing as x to the 6 all over 3. Plus, I don't really like dividing by a fraction, so let's think about it as multiplying by the reciprocal of the denominator. And so flipping that, we would have a 2/3 x, and this is x to the 3/2 power, minus 2x plus c. Okay, and so let's check. We can always check these by going backwards, take the derivative, and make sure when we take that derivative, we're getting back our original function, little h of x. So taking the derivative, right, we would bring down our exponent, subtract 1 from our exponent of 5, that's divided by 3, plus 2/3, bring down our exponent. So that would be a 3/2 subtract 1 from our exponent, so 3/2 minus 1. So 3/2 minus 2/2 is 1/2. Minus the derivative of 2x, well, bringing down an exponent of 1 is -2, subtract the exponent is 0, x to the 0 power is 0. I'm sorry, it's 1, so this is -2. And derivative of a constant is 0. And so if we reduce this, 3 goes into 6 twice. This 2/3 times 3/2, those cancel. And so we're left with this 2x to the 5th, x to the 1/2 power, which we could rewrite as the square root of x, minus 2. Oops. So it checked out. And that's what we wanted to show, that this was the same thing as what we started with when we took the derivative of our antiderivative. So I don't know if you figured out a rule in here while we were going through this. And so there is a rule of how we could take the derivative of these functions when it is a polynomial or radicals in there. So hopefully you saw while we were doing these examples a way that we can come up with a definition of how to take the derivative. So if we have f of x, let's say, is equal to x raised to some exponent n. So let's see if we can come up with a rule here. So the antiderivative of this, so if we took the derivative of this antiderivative, we'd have to get back f of x. And so remember, when we take the derivative, we're bringing down the exponent and subtracting 1. So we know that when we bring down the exponent and subtract 1, we want to get back this just n. So we'd have to add 1 to that n so that when we subtract 1, we get back in. But again, if we take the derivative right now, we bring down that exponent of n plus 1. But we don't have an n plus 1 in front here. So to take care of that, we would have to divide by our new exponent of this n plus 1. And then for now, we're going to add this constant c. So again, if we check this, we take the derivative of the antiderivative. That tells me to bring my exponent down front, which is n plus 1, x to the n plus 1, subtract 1 from my exponent after I take the derivative, or when I'm taking the derivative, and then all over this n plus 1. And the derivative of a constant again is 0. So simplifying, those n plus 1s in the numerator and denominator, because it's multiplication in between, those cancel. And we're left with x raised to the nth. I don't have to add that plus 0. So the derivative of our antiderivative was equal to our original function, f of x. So we came up with a rule. A power rule for our antiderivatives. Okay, let's see. So let's look at some notation here. So there's another way that we can write this without just saying every time I'm taking the antiderivative of this. So let's look at the following. You know, there's a lot of words. Let me blow this up a little bit and talk about it. Okay, so for notation, if we take the differential form of the derivative, so remember we could rewrite taking the derivative dy dx equals f of x. And we rewrite it in the form of dy equals f of x dx. So we were looking at differential equations where we were looking at that back in the beginning of chapter 4 somewhere. We can find the antiderivative of both sides using the integration symbol. So this integration symbol looks like an elongated S. So whenever we see that elongated S, that is telling me we're going to take the integral, or we're taking the antiderivative. Okay, so that is, if we have y equals the integral of dy, I'm sorry, if this is equal to y, the integral of f of x dx, which we could say is equal to capital F of x plus some constant c. So each piece of this equation has a name that I'll refer to. So what we're taking the integral of, this f of x function, this is called the integrand. The variable that we're taking the antiderivative with respect to, that has to do with this dx. So this tells me that I'm going to integrate with respect to x. We had just talked about that the antiderivative of little f of x, we could denote by capital F of x. So we can say this is the same thing, capital F of x is equal to this. But because of that constant c, right now, we're going to have to add on that constant c. So really, let me write it on the other side. So this is equal to our capital F of x plus some constant c. So the term of the indefinite integral is a synonym for antiderivative. So just like there was just different names that we could say for taking the derivative, y prime dy dx. This is another way of saying we're integrating. We're taking the antiderivative. This is a definite or indefinite integral. Right now we're working with indefinite integrals. Later on, and I'll tell you about it later, that we'll work with what is called definite integrals. This c, if we're dealing with some real life application, then we will probably be able to figure out what this constant c is. So let's just talk about why we have that c there. If you're thinking about derivative, remember when you take the derivative, that is telling us the slope of a tangent line at any point on our graph of our function f of x that is differentiable. So technically, let's just look at a parabola x squared. If I looked at this and I took my tangent line at some point x, and I look at x right here, and I look at that tangent line. That's not on my tangent line, so I'm going to move this one other. Let's say it's right here. Well, if I do a transformation, remember adding a constant or subtracting a constant to a function f of x, all that did was it took our graph and it transformed it, shifted it vertically up or vertically down, depending on if you were adding or subtracting a constant. And so if we took this parabola shape and we shifted it up c units, and that c could be any value, this would be the same shape as this. And basically, when we look at the derivative function, and I wish I could do this better and draw better, at that x equals c, this right here, these should be parallel lines. And so adding any constant c, we're always going to have that same slope or subtracting some constant c, you're going to always have that same slope of that particular value of x anywhere on that graph, right? That vertex is always going to be what x equals 0 if I shift it up or down. So that's why we have that c value in there. If it was some particular equation, then it's going to give us enough information that we know a point on the graph. And so we could figure out what that c, that constant is. Okay, so let's start looking at some examples. So in front of you are some of those basic antiderivative rules or integration rules. If we have the integral of 0 dx, so thinking about what can we take the derivative of and get back 0, well, taking the derivative of a constant gives us back 0. So the integral of 0 dx is just a constant c. Let's say we were taking the integral, the antiderivative of k dx, where k is equal to a constant, some number that doesn't change. And so if we take the derivative, let's say, or antiderivative of 2. So in order to get back 2, when I take the derivative, it would be 2x. And so if we have the antiderivative of a constant, k dx, this would be equal to k times x plus some constant c. Well, if we have that coefficient, just like when we're taking derivatives, if we had a coefficient in front of our variable, we kind of ignored that coefficient and we just took the derivative of that variable piece of the derivative or of that term, and we would just multiply it by that constant. So same sort of idea here. If we have the antiderivative of k times f of x dx, then we can think of it as, let's pull that constant in front before we take the antiderivative, and then let's take the antiderivative of f of x. So if I wanted to rewrite this a little bit more, this is the same thing as k times, if I'm taking the antiderivative of little f of x, I would denote it with a capital F of x plus some c. If we have more than one term, we can think of it as adding different functions. And so if we take the antiderivative of more than one term, then we can think of it as taking the antiderivative of some function. The first term is f of x plus or minus the second term, we'll call it g of x, d of x. And this would be equal to the antiderivative of the first term, f of x dx, plus or minus the antiderivative of the second term, g of x. And then there's one other one, and we came up with this, but I forgot to put the stipulation on. So the antiderivative of x raised to some exponent of n and some constant or real number. Then taking the antiderivative, we add 1 to the exponent, divide by our new exponent n plus 1, add our constant c. But we say that n can't be -1 when we start. So let's just talk about that. Let's say that n was -1. If n was -1, so if this was x to the -1 power dx, this is the same thing, right, as the integral of 1 over x dx. So think back, what could we take a derivative of to get back 1 over x? So hopefully it's coming to your head. But remember, if we took the natural derivative of the natural log of x, it would be 1 over what we were taking the natural log of, in this case x. So it would be 1 over x times the derivative of x, which is 1. We have to be a little bit careful here because of our domain of natural log. And so then let's put on these absolute values. Plus c. So here's another rule. That's why n can't be -1. Any other exponent other than an exponent of -1, this rule works. But if it is -1, the antiderivative of 1 over x dx is equal to the natural log of x plus c. Okay, so let's use this. So let's say we have the integral of the cubed root of x, oops, cubed root of x dx. So just like when we were taking the derivative of a function, sometimes it was helpful for us to rewrite the function. So same sort of idea here. So the integrand, which is the cubed root of x, let's rewrite it as x raised to the 1/3 power dx. Okay, so our exponent is not -1, and so we're going to use that rule where when we take the antiderivative of that integrand, we're going to add 1 to our exponent. So it's going to be 1/3 plus 1, 3/3. Divide by our new exponent. So this is going to be the 1/3 plus 1, which is 3/3, plus some constant c. So cleaning it up. So I have x to the 1/3 plus 3/3 is 4/3. So that means I'm dividing by a 4/3 plus c. So x to the 4/3 times the reciprocal of our denominator. So my coefficient in front is really just 3/4 plus c. So my antiderivative of the cubed root of x is equal to 3/4 x to the 4/3 plus c. What if it was 1 over, let's say 4x squared dx? So same idea, we want to rewrite this so it's in a form that we're recognizable and can take the antiderivative of. So let's rewrite that integram. Let's bring up x squared into the numerator by making that exponent negative. So this is the same thing as 1/4 x raised to the -2 power dx. Rules of integration, and normally I won't do this, but normally this is telling me I could bring this 1/4 outside of this integral, x raised to the -2 dx. So bring down our 1/4. Now when we take the antiderivative of x to the -2 power, we're adding 1 to our exponent, so -2 plus 1. Divide by our new exponent. Well, that would be -1 plus some constant c. So let's bring that negative out front. This is -1/4 x raised to the -2 plus 1 power is -1 exponent plus c. So because we started with our integram with that variable down in the denominator, I would rewrite this, bringing down that piece with a negative exponent to make the exponent positive. We have -1 all over x to the first power. I don't have to write that. I need that 4 in front too. So -1 over 4x plus c. So again, all of these we can go backwards, take the derivative of what we found. And if we take the derivative of what we found, we should get back our integrand. Okay, let's say we're given that we have the integral of x squared plus 2x minus 3 all over x to the 4th dx. So again, looking at this, we're manipulating this so that we can take the antiderivative. Before, when we started, if we had something like this and we needed to take the derivative, we didn't know the quotient rule. And so remember how we rewrote this as a sum of multiple fractions. So we could just divide each term by that x to the 4th power, right? And so this is the same thing as saying x squared over x to the 4th plus 2x all over x to the 4th minus 3 all over x to the 4th dx. And so we can simplify. And so this is the same thing. Well, x squared over x to the 4th, that's 1 over x squared. Plus 2x over x to the 4th is 2 over x cubed. Minus 3 over x to the 4th dx. So just like that last example where we brought our terms up to make that exponents negative. So we didn't have any variables in the denominator. So we could rewrite this as x to the negative 2 power plus 2x to the negative 3rd power minus 3x to the negative 4th power dx. So again, I technically wouldn't rewrite this, but this is, we are technically saying this is the same thing as the antiderivative or integral, indefinite integral of x to the negative 2 dx plus 2 times the integral of x to the negative 3 dx minus 3 times the integral of x to the negative 4 dx. And so now we can just apply the rule, add 1 to the exponent, divide by our new exponent. So just like with derivatives, we wrote it out for a little bit at first, but now let's just start doing it. So adding 1 to negative 2, that gets me negative 1, divide by our new exponent of negative 1. Plus 2x raised to the, add 1 to our exponent of negative 3, that gives us negative 4. We're dividing by our new exponent of negative 4. Minus 3, so taking the antiderivative of x to the negative 4, add 1 to our exponent. I made a mistake. If I add 1 to negative 3, what do I get? Not negative 4. So this is where you got to be careful because we're so used to subtracting 1 from our exponent. Okay, so adding 1 to negative 3, we get negative 2. So divide by our new exponent, negative 2. Add 1 to our new exponent, or our exponent of negative 4. That's going to give me negative 3. Divide by that new exponent of negative 3. Plus some constant c. Really, when we took the antiderivative of each piece, we added a constant c. But if we added a constant c to each piece, a constant plus a constant plus a constant is still a constant. So we're just going to just add one c there. We don't have to add multiple c's there. So this is our antiderivative, and then you would just go through and clean it up, giving it positive exponents and simplifying where possible. And so we could rewrite this as negative 1 over x. Notice the 2's cancel. So this is negative 1 over, I can bring that x squared down. 3's cancel, 2 negatives make it a positive. 1 over x cubed plus c. I'm okay with you leaving like that. You could technically, if you wanted to, go through and we could get a common denominator and rewrite that as a single fraction. So our next example, we have integral of the quantity 2t squared minus 1, and that whole quantity is squared dt. And so notice that that is dt. That integrand has a variable with t. And so it's saying that we're integrating this with respect to t, not x this time. We do not know how to take the antiderivative of this, but we do know how to do it if we expanded that 2t squared minus 1 times 2t squared minus 1. Right, and so we could just distribute and figure out what that is and rewrite our integrand. And so if we distribute, we got a 2t squared times the 2t squared is a 4t to the 4th. We're going to have a negative 2t squared minus another 2t squared. That's a negative 4t squared. And negative 1 times negative 1 gives us that plus 1. So we can rewrite our integrand as 4t to the 4th minus 4t squared plus 1 dt. So just like we were taking derivatives of multiple terms, we didn't rewrite that, oh, we're going to take the derivative of each term. I'm not going to rewrite this each time saying I'm taking the antiderivative of each term. I'm just going to go ahead and do it. And so if I took the antiderivative of 4t to the 4th, we're going to add 1 to our exponent. So we now have 4t to the 5th power, divide by my new exponent of 5. Minus 4t, add 1 to my exponent. So adding 1 to 2 is 3, divide by my new exponent of 3. Plus the antiderivative of a constant is the variable what we're taking the antiderivative of. So that would just be t. And then we're going to add some constant c. And so see if that simplifies at all. It doesn't look like it. So the antiderivative, if we call that little f of t, is capital F of t is equal to 4/5 t to the 5th minus 4/3 t to the t cubed plus t plus c. Okay, let's throw a trig in there because I know how much you guys love the trig. Well, let's say you wanted to take the antiderivative of cosine of x. And so you have to think to yourself, what can I take the derivative of to get back just cosine of x? Well, isn't that just sine x? Derivative of sine x is cosine x. So the derivative, antiderivative of cosine x is just going to be sine x dx. Oops, not dx. Plus c. Okay, well, what about antiderivative of sine of x, or the indefinite integral of sine of x dx? Well, what we take the derivative of to get sine x, if we took the derivative of cosine x, that is negative sine of x. And so I don't want the negative in front of that. And so I would need to take the antiderivative of sine of x is going to be negative cosine of x plus c. Because again, if we take the derivative of a trig function that starts with co, we take the negative of that. So the negative of this negative would make this a positive sine of x. So what if it was the antiderivative of secant squared x dx? So think about which trig function, when you take the derivative of, is secant squared x. And that one is tangent x plus some constant c. So we could go through each one of these. So I have to kind of think backwards. So if I was looking at the antiderivative of cotangent, that was cosecant squared. So if we're looking at the antiderivative of cosecant squared dx, that is cotangent of x plus c. If I was looking at the antiderivative of secant x tan x dx, before I do that one, I need to be careful of this one right here. Taking the derivative of cotangent, that would have given me back a negative cosecant squared. And so I need the negative in front of this cotangent. Derivative of secant x tan x, the one that gave that to us was secant x. Let's see. And cosecant x cotangent x dx. So the one that gives us that is negative cosecant x plus c. So being aware of what those derivative functions look like when you take the derivative, then you can kind of think backwards. We can do that with our inverse trigonometric functions too, but we're not going to have time to do that today. Maybe look at one more. So let's say that we have the antiderivative of theta squared plus secant squared theta. And this is all d theta. So taking the antiderivative of theta squared. So we're taking it with respect to theta. So we're just going to add 1 to our exponent, which would be 3. Divide by the new exponent, which would be 3. Thinking to ourselves, what can we take the derivative of to get back secant squared theta? That would be tangent of tangent of theta. And then we have some plus c. Okay, so we've looked at a lot of the antiderivative and how to take antiderivatives and indefinite integrals. We'll look at a little more of those tomorrow and looking at initial value problems. How can we figure out what c is? We're given a little bit more information, we'll be able to find this constant c that we keep on adding in here. We'll look at some application problems. So going kind of backwards, we knew about motion with position, velocity, acceleration. So given one, acceleration, we can work backwards, taking the antiderivative to get the position function and so on. And then we're going to look at it as integrals as looking at areas under the curve, because it also can represent that. But we might not get through that all tomorrow. We'll see.